All right, section 5 of the notes, lecture. It's going to be a little abstract, but the bottom line is we'll go through this with you. But the intent here is that you're probably not going to understand everything that's being said. Hopefully, though, after we say this, you go back and look at it and you follow me doing the examples, that you'll be a little bit clearer on it. But to reinforce this, after you certainly sit through the lecture, sit through the examples, study the material, you should be ready to go off on your own to do those supplemental problems that are in the notes. You should be. And that's really what we're looking to do. It's almost like you're at the gym and you're there for a reason. You're there to get better at something. All right. And what are you there to get better at? Hopefully pre-calculus. So when you go into, pre-calc 2 and then eventually calculus, that it's going to move forward for you. And I know I said a lot to you. The intent of an education is to move forward. It's not to stagnate and you simply sit there and say, gee whiz, I don't understand anything. That's your intent in life, is to go forward, to move forward. All right. So we'll talk through this, and I'll certainly go to the whiteboard to partially do that. We'll talk about compositions. We'll talk about additions, subtractions, and multiplications and divisions of functions. But for the most part, people do have trouble with the compositions. The big problem, though, I'll be honest with you, it really boils down to that domain range business. All right. And I'm not saying that everyone is going to get perfect at it, but you'll improve over time. You will. You get better at it. Everyone stumbles, though. So don't feel that you're not up to snuff if you're stumbling through this stuff over here. It's not easy stuff to get through. We'll talk about what one-to-one is, how to invert a function, what an inverse means, yada, yada, yada. We have visual problems. And for the most part, I do like to try to visualize what's going on. All right. Again, we'll go through example questions. The point of the example questions is to reinforce what was discussed in the lectures. And lectures here are going to be really brief. All right. Typically, when you transfer, I'm going to say like a typical university, lectures are never brief. They're really long and they're really devoid of example. They basically go over theory. Sometimes they just do a lot of proofs at the board. And then the thing about that is you go back home and you have to study that material. And that's where a textbook comes into play, that you start reading a textbook. And certainly, I'm not saying the textbook the teacher assigned, any textbook. The more textbooks you have access to, the easier the material becomes. Now, I'm not saying that people are at that level where they're actually reading a textbook at this point, but you want to start moving towards that level. It's not so much as a hand-me-down where I'm actually telling you just by verbal description what things are. You get a book, you start reading it, you're going to start to realize that there's a whole new universe out there of pretty elaborate information. And we're just kind of like glancing on the surface here, actually just touching the surface. We're not going much beneath the surface. All right, so I'm going to do another share with you. I'm going to share a whiteboard with you. All right, so we're on the whiteboard, and I want to just simply, go through some typical stuff that's on the whiteboard at this point. So I'm going to say after you finished this section of the notes, what does that mean? Attended lecture and listened to lecture, studied the lecture material, attended the example session, then went back over the example section to make sure you understood what was presented to you. It should reinforce what was learned in the lecture. Then you're going to do the supplemental exercises. And then after all that stuff is done, which should take a considerable amount of study time, you're going to do the web assignment. All right. So let me outline that for you. So that's after you finish all the material in this section over here. You're going to go to that Math 119 week 5 and web assignment and do it. Also, try to contribute something to the weekly discussion group. I realize somebody say, I have nothing to contribute. And that's unfortunate. You realize that that's most people's goals in life, is to contribute something to their community. And that's what you want to do. You want to contribute something. And you're supposed to be in an academic community. You should be contributing something to the academic community. All right. Now, granted, you may say, I'm not at that level yet. You want to get that level where you're contributing to it. All right. So I'm going to say, make some kind of entry into the weekly discussion group. All right. So let's talk about, the combinations and compositions. So combinations and compositions. All right. A function. So we're dealing with functions over here. So it says, the first thing it says, sums differences, products, and quotients of functions. So it says let f and g, I can see that clearly, I can read, let f and g be two functions with overlapping domains. What does that mean? They have something in common. Their domains have something in common. These functions need something in common. Their domains need to be in common, not their entire domains, just overlapping, that they share something together in their domains. All right. Then for all common x in the domains, and what does that mean? Where they intersect. All right, where their domains are intersecting. The sums, differences, and products and quotients of f and g are defined as follows. And they're pretty straightforward. So how's a sum defined? Well, a sum is defined as f plus g. All you got to do is add the functions together. What's a domain? It's the intersection between f and g. And we'll go through examples. How about difference? What's difference going to be for two functions that have overlapping domains? Well, it's written this way over here. What are we doing over there? We're just subtracting those two functions. Now, subtraction is not commutative. Addition is, though. This is important in order in what you do it in. Here's the deal, though. It's still the intersection of the domains of f and g. That's pretty reasonable. All right, how about products? Well, really, it's sort of like defined. Like if someone says product, well, we're just taking the product of two functions. What's their domain? Again, it's the intersection of f and g. That's where they overlap. All right. Quotient's a little bit sticky, and I'll tell you why. There's always that chance of a division by zero. But how do you do a quotient? Well, a quotient is just simply f divided by g, provided the g is not equal to zero. So I'm going to say it's still the intersection of f and g, but now we must exclude the x's in the domain of g where g would produce a zero. And we got to be careful of that, right? We have to be careful. And here comes a tough one. I'm going to say that, sums, differences, products, and quotients tend to be easy. What students find difficult, they find this FOG, and some students actually mispronounce it as FOG-X. It's not FOG. It's read as F of G of X. It's a composition. Okay, that's a little circle there. F of G of X. I personally do not like the notation F of G of X. I just don't like it. So what I prefer to write down instead is F is being composed with G. I actually prefer to write that down. And you'll see me do that when I'm doing problems over here. So it says, the composition function is a bit more difficult. Yeah, it is. And here you're going to have to work over some pretty vexing concepts. Don't despair, though. What are we trying to get you to do? Try. I kid you not. We're trying to get you to try. Okay. So I'm going to say that's the way it's going to be written as F of G of X. All right, here comes the tricky part. It's this domain thing. All right. The domain, whoops, sorry about that. The domain of this composition F of J is the set of all X in the domain of J such that G of X, i.e. its range, is in a domain of F. So I can apply what's going on over here. G has a domain but what G attempts to do, G attempts to give it, which is its range, to F. And this is G's range. The problem for this, though, is F may not be able to accept those numbers that G is given it. So what we typically have to do is we have to be very careful to exclude any elements in the domain of G that would produce a range number in G that F would choke on. And that's going to be a little scary for students to do. Some students collapse at this point. They say they can't do it. We're saying give it a try. We'll go through examples. It sounds scary. It really does. But we'll see in the examples to follow that it just requires a little patience on your end. And in education, does require patience, by the way. All right, let's keep going. Okay. Next topic, this inverse function business. All right, let's read the definition. Again, we're on inverses. And we're on a definition now. Okay. The word, I hate to say, sometimes these words, they get so confusing to students that they have no idea what they've been given. So I have to claim when I'm doing this over here, I really have to boil it down to some kind of simple, picture story. And I'm not going to say that's the worst thing in the world to do, but whenever you're reading a story, I'd say you should be able to visualize what they're saying. And I'm going to read it to you. It says, a function f is called one-to-one if it never takes on the same value twice. That is, whenever x1 is not equal to x2. So someone says, what does that, what does that mean? And I got to go over that with you. So it says, we can awfully visually verify that a function is one-to-one by using a horizontal line test, which states, let's go through this. A function is one-to-one if and only if no horizontal line intersects the graph more than once. You know what? That's what that sentence above says. A function f is called one-to-one if it never takes on the same value twice. That is, f of x1 never equals f of x2, provided x1 is not equal to x2. Well, let's put our horizontal line test in. And what am I seeing over here? There's a horizontal line. What am I seeing? It's pumping back 3 different answers. I'm sorry, three answers that are the same, but for different x values. Let me point that out to you. This is an x value. This is an x value, which is different than the other one. And this is an x value, which is different than the other one. What are we saying? F of x1 is identical to f of x2 is identical to f of x3. So this function is not one-to-one. How do we determine that? Well, if you knew the definition, that's fine. But here's the deal. I think for most students, the definition is very cumbersome. So we use what's called the horizontal line test. It's clearly not one-to-one. What's the problem with this test? You need a picture, and the picture better be clear as day. Unfortunately, sometimes pictures can be very deceiving. Very deceiving. All right, so that's an example. It's an example of a function that's not one-to-one. Relatively straightforward. I want to claim over here, though, that a lot of students say, are you going to really, give me things that I can't visualize? And, I'm not going to say yes, but, it could happen, and be aware of that. And if you want to read through this, you can. It's a little more complicated, but, it can't hurt to look at it. All right, let's go to the next definition. And I'll read it to you. All right, definition. Whoops, did it again, didn't I? Definition. Let f be a one-to-one function. Now, what does that mean? That f would pass the horizontal line test. Now, what does that mean? I could draw a horizontal line, and it's going to hit the curve at most once. With a domain A and a range B. So f must be one-to-one with a domain A and a range B. Then it goes on to say it has an inverse. Its inverse is denoted by this thing over here. Now, unfortunately for a lot of students, they're reading that and they see this f minus 1 and they think this means reciprocal. This has nothing to do with reciprocal. This has to do with an inverse. This is read as the inverse of f. All right. And again, we'll go to examples. Now, what does it say the inverse of f is? It says it has a domain B. So I'm going to say if it has a domain B, That was the range of f. So what happened is the range now becomes the domain in the inverse. And the domain A of f now becomes the range of f inverse. So what I'm going to claim over here is appears to be a rotation. Domain becomes range, and range becomes domain. So what I'm going to tell you over here is that this is basically just a rotation through the XY line. And we'll go through examples of that. All right. They write this stuff over here. F inverse of y would give you x. F of x gives you y. I'm going to say this again. X becomes y becomes x. Okay, here comes the tough part for students. When we do this, the first thing we got to do is determine if f is 1-to-1, what is its domain, and what is its range. So the first thing we're going to be looking for is we're going to be given a function f. Whoops, sorry about that. We're going to be given a function f. You need to determine that it's 1-to-1. You can do this visually. You need to determine its domain, and you need to determine its range. And then they're going to ask you to find its inverse. And we've got a method for it. And the method is what's going to follow over here on the next page. Our method is going to be this method over here. Now, someone's going to say, does this method always work? No, it doesn't always work. But I'll be honest with you, it would be awful to give you problems that were not working. All right, so let's go to the next page. And I'll outline the procedure for you. All right. I'll talk about that graph in a second, by the way. The procedure is going to be basically a 4-step process. All right. And it's going to be, there's going to be number 1. It's going to be number 2. We'll go through examples 2, number 3, and number 4. All right. So I'm going to just outline what we're going to be basically doing over here. And again, I can't say it's not, it's so important, that we need to know domain and range for this as well. That's specified in the prior page. But the first thing you're going to do is in the equation for f of x, replace f of x by y. And yes, we'll go through examples. So when you see the equation for f of x, all you have to do now is replace f of x by y. But let me repeat this. You need to know the domain of f, and you need to know the range of f before you do this. And you certainly need to know that f is 1. Whoops, I didn't mean to put that down. 1-to-1. That's so important. So you need to know f is 1-to-1, and you need to know its domain and its range before you proceed forward. All right, what's the next thing you're going to do? Interchange the roles of x and y. Well, I can't say that's enough time. What we're really basically doing is rotating about a line x equals y. All right? So interchange the roles of x and y, and then solve for y. What's the next thing you're going to do? Replace y by that notation f inverse in the new equation. And yes, we will go through examples. Although not necessary, it may be a good idea to verify the following. Generally speaking, I don't do that. All right? So here's the deal. You're going to give it a function f, make sure it's 1-to-1, determine its domain and range, and follow these steps. First step, replace f of x by y. The second step, interchange the roles of x and y and solve for y. The third step, replace y by that notation f inverse of x. Here's the deal though. At the very end, you should also specify the domain and the range of this. And how do you do that? Well, if you know the domain here, this would become the range over here. And if you know the range here, it would become the domain over here. So again, I'm going to claim over here that an inverse is just a rotation about the line y equals x. Well, remember, domain is x and range is y. So what are we doing? We're rotating those two. Range becomes domain, domain becomes range. Right. Well, look at a picture that's deceptive. Right. This is actually a graph of an invertible one-to-one function. This graph here, f of x, is actually a one-to-one function. And the graph is the graph of this thing over here. So let me write that down for you. This is 1 to 1. Now, I'm not saying you're at the level where you could show that, but on the prior page, that's what we talked through. So what I want to do is I want to tell you why this is so deceptive. If I'm looking at this over here, I'm going to say, once I get in this region over here, by the way, once I get beyond that, I'm pretty clear it passes the horizontal line test. Whoops, I'm sorry, that didn't do that. I should not have done that. Stop there. All right. What I'm going to do is I'm going to blow this region up here. And this is where a lot of students get horribly confused. Like they say, I think I could draw a horizontal line here that hits it more than once. And this is what's known as an artifact of looking at the picture. The problem with this picture over here is that it looks like it's flat, but this thing here, and I'm gonna just circle it for you. This whole thing over here is always increasing. You should realize if it's always increasing, a horizontal line, if it's always increasing, would only puncture it once. Now, the deal about this over here, I have to tell you something. It's a really slow increase, though. This is something you learn more about calculus. As opposed to these things over here, this is a very clear increasing function over there. Very clear. Horizontal lines very clearly hit it once. I got to tell you that over here, this is where students get horribly confused, right? They think it's horizontal there. It is not horizontal. It's always moving up, always moving up. Although slowly, it's always moving up. It's always increasing. When you take calculus, that's pretty easy to show. But right now, it's sufficient to accept it from me that this is a one-to-one function. And in fact, it does pass the horizontal line test because it can be shown that this function is always increasing on its domain, which is a big issue for invertibility. We want them to be always increasing on their domain. All right, so I'm going to say that pretty much covers it. And then we need to go to do examples. All right, let me stop.